Okay, class, welcome back. Today, it's all about section 3. And what is section 3? Logarithmic functions. So logarithmic functions are the inverse functions of exponential functions. So you're going to see those come back here, but so they're directly related to each other. And so since they are inverse functions, you're also going to remember from the first section on um, inverses, everything applies here as well. Okay, so the previous section dealt with exponential functions of the form a to the x, where a is not equal to 1 and positive. And the horizontal test shows that the exponential functions are 1 to 1 and thus have inverse functions, right? Those inverse functions are what we call the logarithmic functions, right? So we're going to found by interchanging x and y, right? So we're going to go through those steps, and then we're going to solve for y, and then that's going to be the inverse function. So we start by y equals a to the x, and we're going to switch them and get x equals a to the y, and now we're going to solve for y. Okay. So y is an exponent, so that must be raised in order to obtain x. Right? We call the exponent a logarithm, symbolized by the abbreviation log. The expression log base a of x represents the logarithm in this discussion. Okay? So this is an exponent. This is equal to y. Okay? The number a is called the base, like I just said, of the logarithm. X is called the argument, right? This is a function, log function, so x is the argument of the expression, and it is read logarithm with base a of x, or logarithm of x with base a, or base a logarithm of x, however you want to say it. Okay, so logarithm for all real numbers y and all positive numbers a and x, and again, we don't want a to be equal to 1, then y equals log base a of x is if and only if, so this is true, if and only if x is equal to a to the y. Okay, so this goes both ways. So now we've got a way we can write any exponential equation as a logarithmic equation, or we can go back and forth. We can take a log and write it as an exponential. Okay? The expression log base a of x represents the exponent to which a base must be raised in order to obtain x. So in other words, we want to ask ourselves the question, if we want to solve for y, we have to ask ourselves, okay, what exponent do we need to raise a to in order to get x? That answer is y. Okay? So here's the exponential form. Here's the logarithmic form. So 2 raised to the third power is equal to 8. 1/2 raised to the negative fourth power is equal to 16. 10 raised to the 100th, or excuse me, the fifth power is 100,000. 3 raised to the negative fourth power is 1 over 81. 5 raised to the power of 1 is 5. 3/4 raised to the 0 power is 1. To remember the relationship among a, x, and y in the two equivalent functions, refer to these diagrams. Okay? Logarithmic form. Y equals log base a of x. So exponent, base. Okay? Here the exponential form, we have a to the y equals x. This is the base, exponent. Okay? So let's solve this. Solve each equation. So we have log base x of 8/27 equals 3. So in other words, well, how do we solve this? Well, x raised to the third power equals 8/27. Right? So let's write it in exponential form. And so now that we have an exponential form, Now we can look at how can we rewrite this as something raised to the third power. Well, this is 2 to the third, and this is 3 to the third. So we can write this as 2/3 raised to the third power. And now x to the third is equal to 2/3 to the third, and that means the bases, in order for this to be equal, the bases must be the same. And so x equals 2/3, because if we take the cube root of both sides, we get x equals 2/3. Okay, and if we check, all we have to do is plug in the value, 2/3, right? So stick it in our calculator. So again, exponential, right? 2/3 raised to the third power equals 8/27. And it's true. Okay, now what about this one? So to solve this one, we're saying 4 raised to this power equals x. So all we have to do is write it in exponential form. 4 raised to the 5/2 power. So this will be 2 to the 5th, which will give us 32. Now what about this one? Okay, well, x equals this. We've got log base 49. How are we going to solve this one? Well, it seems like we're solving for x, but this is a complicated looking log. Let's see if there's a way we can simplify this. Now, if we raise it 49 to the x, right, exponential form is equal to this. Now, all we have to do is, can we make this, the bases the same? Or can we rewrite this so that we get something like this over here? Well, here, this is equal to 7 squared. This is equal to 7 to the 1/3 power. So now we've got the same base. And so this is 2x, right? A power raised to a power. So 7 to the 2x power is equal to 7 to the 1/3. That means 2x has to equal 1/3. And now we can solve, and we get x is equal to 1/6 by using our properties. Okay, so the logarithmic function, if a is greater than 0, but again not equal to 1, and x is greater than 0, then the logarithmic function with base a is given by this formula. So this is the form of a logarithmic function. And notice that it is the inverse of the exponential function, right? So here's the log function. Log base 2 of x is the inverse of 2 to the x. Okay. Now, since they're inverses of each other, these 3 points that we talked about in exponential form is they're flipped, right? So when we reflect them across the y equals x axis, well, if this goes through -1, 1 over a, 0, 1, and 1, a, then when we do this, it's going to flip these. So this is going to be 1/2, -1, or 1 over a, -1. This will be 1, 0, and then a, 1. Okay? And then, again, the domain and the range flip. So we know the domain of this is going to be all positive numbers, and the range is now going to be all real numbers for the log. So we can use the information we learned about inverse functions to really help us. So we don't have to memorize a lot here. If we know the exponential functions, we know the characteristics of the exponential function, we can use what we know about inverse functions and easily get the information for logs. Okay, so you can see here, so this is log base a of x. The domain is 0 to infinity, or all the non-negative numbers, or all positive numbers, I should say. And then all real numbers for the range. And so notice that it always goes through these 3 points. Okay, and it's also increasing and continuous on the entire domain. And this time now, the y-axis is the vertical asymptote. Okay, so again, logarithmic functions of this type always go through these 3 points. And again, if you replace it with negative x, or excuse me, I'm sorry, with between a is between 0 and 1, then you get a reflection across the x-axis, as so. So again, now you've got a decreasing function. Okay, it'll still go through the same points. Okay, a comma 1, 1 comma 0, and 1 over a comma negative 1. Hold on a second, there's a... Yeah, okay, just want to make sure that there wasn't a typo. Okay, and the vertical axis, asymptote as x approaches 0 from the right. So as x approaches 0, it goes closer and closer to the y-axis. Okay, so here are the characteristics of the graph. Okay, so these are the characteristics to remember. So the points 1 over a comma negative 1, 1 comma 0, and a comma 1 are on the graph. If a is greater than 1, then it's an increasing function. If you're between 0 and 1, f is a decreasing function. The y-axis is now the vertical asymptote, and the domain is all positive real numbers and all real numbers for the range. So now if we want to graph these, we're going to do the exact same thing we did before with the exponential functions. Okay, so we're going to have an idea. We're going to graph this function here, which defines the inverse of the function, right? And then we can use the reflection across y equals x in order to get the function we're looking for, which is the logarithmic function. So if you notice here, here's our x values. Here are the y values for the exponential function. And now once we know these here, these three points here, then we know that this logarithmic function is going to be the reverse of these two. So it'll be 1/2 comma 1, 1/4 comma 2, and 1/2 comma 1, 1 comma 0, and 2 comma negative 1. And so this is what we get. Okay? So here's the exponential curve, and then when we reflect it, we get the corresponding inverse function, the log function that we want. Okay, now you don't have to do it that way. You could use the characteristics to graph the log function as well. Just remember where the vertical asymptote is located and such. So now if we take this one, we can write this as an exponential form, right? And we know that if we use those 3 points, 1, 0, and negative 1, right, we know that it goes through these 3 points. 1/3 comma negative 1, 1 and 0, and 3 and 1. And so this is what it looks like. Okay? Now, here's a word of caution. If you write a logarithmic function in exponential form to graph it, as in 3b, start first with the y values to calculate the corresponding x values. Okay, let me say that again. Start with the y values to calculate the corresponding x values. Be careful to write the values in the ordered pairs in the correct order. So if we go back here, so again, make sure you're using it correctly here. Okay, so you're going to plug in y to find x. Okay, so notice here, this is what you're thinking, right? So you're plugging in y to find x. Okay, so you're writing in this form, but you're plugging in y to get x. And so that's the way you want to do it. So it's in that case, in that way. Okay, so be careful that you write the values in the ordered pairs in the correct order. Okay, so now what if we want to graph this one? Okay, well, here we've got log base 2 of x minus 1. So again, we're subtracting within the function. So this is going to be a horizontal shift 1 unit to the right. Okay, so what we're going to do is we're going to use the basic function, the basic log function, graph that, and then shift it 1 unit to the right. Okay, so here we go. So here's the expression. Okay, so we wrote it in exponential form. And so now we're right in here. So basically we're going to plug in y, right? So we're going to plug in y and find the corresponding values. Okay, so we first choose the values of y and then calculate each of the corresponding values of x. So if we put in our value of y, okay, again, so what is the value of y we want? We want 2, right? And we get 5. Plug in 1, we get 3. Plug in 0, we get 2. Okay, and then we can sketch the graph. Okay, now in this case here, oh, let me go back. So again, notice that the range is all real numbers, right? The range is all real numbers, but this time because it's shifting 1 unit to the right, remember the vertical asymptote also shifts 1 unit to the right. So that means that the domain of this function is going to be everything from 1 to positive infinity. Okay. Okay, now in this case here, we have this function, this log function, but we're now subtracting 1 from outside the function. So this is going to be a vertical shift down. So again, we're going to focus on this, and we're going to plot this, and then we're going to just move it down to get the transformation. Okay. Okay, so what do? Write in exponential form, right? So we add 1 to both sides, and we get x equals 3 to the y plus 1. So now we're going to add values of y and get the corresponding values of x. And the domain is 0 to 8. No, there's no horizontal shift, so it's 0 to 8. And the range, again, is all real numbers. Okay, and so again, make sure you're plugging in values of y to get the values of x. Okay, right here. So you're going to plug in values of y to get the values of x. So that's opposite of what you would think. So because we're using the exponential form. So if you plug in 2, or if you plug in 1 for y, you get 9. If you plug in 0 for y, you get 3 for x. When you plug in negative 1 for y, you get 1. Okay, and of course this one's including both. So this is base 4. Now we've got a shift to the left 2 units and then up 1 unit. So we're going to focus on writing this in exponential form. And so once we write the first value, right, so we're dealing with this, right, once we know the graph of this, then we can shift it to the left 2 units and then up. And then the domain is going to be found by solving for this, right, because it's shifting to the left 2 units. Okay, so it's going to be everything that's greater than negative 2. Okay, so we'll get the domain of -2 to positive infinity, and of course the range is going to be all real numbers. Okay, and once we do that, then we get this sketch of the graph. Okay. Now the properties of logarithms enable us to change the form of the logarithmic statement so that the products can be converted to sums, quotients can be converted into differences, and powers can be converted into products. So this is the properties of logarithms that are going to help us to solve logarithmic equations. Okay, so here are the properties. So if you have a log of a product, that's equal to the sum of the logs. Okay, the log of the product is equal to the sum of the logs. The log of a quotient is the difference in the logs, the top minus the bottom. Okay, and then if you have an exponent, the property says that you could take the exponent and bring it down and make it as a product of the exponent times the log. Okay, also the logarithm of 1. So if I have a base a, it doesn't matter what base a I have, the log of a of 1 is always equal to 0. And you can see that from the fact that if you write this in exponential form, a to the 0 power is 1. Okay, and that's good for any base. Okay, so the log of 1 is always going to be equal to 0, regardless of the base. Also, the log base a of a is equal to 1. Because if you, again, think of it as in exponential form, a raised to the 1 power is equal to a. So that means that if you have the same base as the argument, if the argument and the base are the same, the log is going to be equal to 1. Those are two important properties we're going to use. So let's look at this. So this is multiplication here. So it's log base 6 of 7 times 9. Okay? So again, rewrite the expression assuming all variables represent positive real numbers with a not equal to 1 and b not equal to 1. Okay? So if we look at this, we can use the sum, the property of sum. So we can write this as a sum of logs. So log base 6 of 7 plus log base 6 of 9. What about this one? Now we have a quotient. So now we can use the quotient rule that says the log base 9 of 15 minus the base of log base 9 of 7. So it's the top minus the bottom. Okay, so the quotient property. Now here we have 8, the square root of 8, or in other words, 8 to the 1/2 power. So we can use this and rewrite this as a power, and then we can write that as 1/2 times log base 5 of 8 using the power property. And we can use a combination. So we have m to the 2nd power, the cube root of that. And so we can write this as a power, which would be 3/2, m to the 3/2 power. And so then we can rewrite this using the power property to be 2/3 log base a of m. And now we can get something that looks very complicated like this, and we can put it all together and write it in an expanded form. And so this would be a quotient, but then we have products here and products here. Okay, and with some exponents. Now, this would equal log base a of m plus log base a of n plus log base a of q. That takes care of the top. Minus the entire bottom. So we're going to have parentheses around here because we're subtracting the log of the entire bottom. Okay? So that means minus the log base a of p squared plus the log base a of t to the 4th. Now notice that I could distribute this negative and just do minus this minus that. We could do that as well. Okay, but now I'm going to use the power property here to bring the 2 down in front here and bring the 4 down in front here. And then finally distribute the signs. Okay, just make sure you're careful when you distribute the signs. Now, since there are no exponents, no products, no quotients, we are done. Nothing else can be done with this. So it's been completely expanded. Now we can do the same thing here. Okay, So again, we can write this as log base b of this raised to the 1 over nth power, right? So we can use the product there. And now we can bring this down to here. Well, how can we do that? Yeah, we could do it that way. Or we could distribute the 1 over n to all of these. Okay, so they decided to bring it down. So now what we're going to do is now handle the top and the bottom. So it's going to be this minus this, and then we're going to use the product property here. Okay, so it's going to be 1 over n times the quantity log base b x to the third plus log base b of y to the fifth minus log base b of z to the n. And now we've got to take care of these exponents and bring them down. And so we're going to get 3, 5, and minus m. Okay, so we brought all the exponents down, and now we can distribute the 1 over n. And so we get 3 over n log base b of x, 5 over n log base b of y, minus m over n log base b of z. Okay, now we can go the other way. We can go from expanded to condensed, I guess, if you will. So we can collapse it and write it as a single logarithm. Okay, so now we can go the other way. So now the key thing is these all have to be the same base in order to use these. Okay, so now we've got a plus, so we can write this as a product. We've got a subtraction, so this is going to be a quotient. Okay, so we can rewrite these two as a product, and then the minus becomes a quotient, so it goes on the bottom. Okay, so then we can write this as the log base 3 of the entire quantity of x plus 2 quantity times x divided by 2. Okay, what about this one? So now we've got a 2 here and a 3 here, so these are going to go back up as exponents, and then the minus sign means we're going to take the quotient of the arguments. Okay, and so here's what we have, right? So this becomes this, and then now we're going to deal with the difference or the quotient property. Okay, and we get final answer is this. So we got a 1 log, and we're done. Okay, so now we've got these. Okay, so how would we handle this? So we've got plus, we've got some coefficients, which are going to become the exponents. Okay, and so when we've got subtraction. So first thing is, take care of the exponents. So that 1/2 goes to here, 3/2 goes to here, but make sure you put parentheses because the whole thing is the argument. So put parentheses around here. Okay, and then of course this doesn't have a coefficient other than 1, so that'll stay the same. Okay, and next we're going to deal with the plus and minus, and we get the final property or the final result. Okay, so we do use the distributive property for the 2, and we get 2 to the 3/2 n to the 1/2 because we had to cancel here, right? Cancel here. And then m cancels here because we have to use the property of exponents, rules of exponents here. So we get 1/2 minus 2, okay, which gives us this. And so this becomes our final result here. Okay? Oh, I guess I'm wrong. No. Oh, yeah, I guess we could split this up still. So we pulled out 1/2 because we have whole number exponents here, and then we can change this into a square root. And there we go. I think that should be it. Yes. Okay. Now, there is no property of logarithms to rewrite a logarithm of a sum or difference. Okay? So let me say that again. There is no property of logarithms to rewrite a logarithm of a sum or difference. That is why in the example 6a, this is not the same as this. So we cannot distribute the log across the plus. There's no such property. Okay? this is not the same as this. So be aware. It's a function, right? This is the argument of a function. You cannot do that. Okay, this is inside the log function. Okay, let's assume that the log base 10 of 2 is approximately equal to this. Find each logarithm without using the calculator. Okay, well, let's see what we can do. This is 2 squared, right? So we can write this as 2 squared and then use the power property, right? And so now we know log base 10 of 2 is equal to this. So 2 times this is 0.6020. Okay, what about this one? Okay, well, let's see here. Can I write this as a power of 2? Well, let's see here. We might be able to do that. Well, we get 2 over 10, right? So 5 can be written as 10 divided by 2. And so now we can use the quotient rule. And look at that. Log base 10 of 10. What's log base 10 of 10? Well, that's going to be 1, right? That's always equal to 1 because the base and the argument are the same. So this is going to be 1. And then this, of course, is what? 0.3020. And so 1 minus 0.3020 is point what? 0.6990. So then we have the theorem on inverses. So for a greater than 0 but not equal to 1, the following properties will hold for inverses. Log a raised to the log base a of x is equal to x. Okay, so a base raised to a log of the same base cancel each other out and give us a, because we're taking the exponential of an inverse. So if you take an inverse function and the exponential, okay, so since we're taking an inverse function and composing with the exponential, we're going to get x out. Also, if we do it the other way, if we take log base a of an exponential, so we stick the same base here, then this log is going to cancel with the exponential, and we're going to get x. So both of these work for the theorem of inverses when a is greater than 0 and not equal to 1. So here are some examples. So if we use 7 log base 7 of 10, well, this exponential is going to cancel with this log, and 10 is going to come out. Okay, now in the second one here, we got the log base 5, so the bases match. So remember, log base 5 of 5, the exponent drops out, so this becomes 3. And then here, log base r with r, so the bases match, and it's an exponential form, so the exponent comes out. Okay, so again, if the bases match and you've got an exponential within a log, or a log within an exponential, they cancel out, and this comes out here. Okay, these here, the exponent comes out, here the argument comes out. Okay. Okay, well, that's the end of this section, so please make sure you go through the examples on your own in the PowerPoints and that you know how to do them on your own. Make sure you do the other examples. Make sure you do the exercises in the back of the book. If you get stuck on anything, please bring those to class or email me so that I can work on those in class with you guys, and I could show you how to do that. Again, practice makes perfect, or well, practice makes improvement. So keep doing this, and I'll see you next time.